In the 1600s, two mathematicians, Newton and Leibniz, from two different countries, simultaneously discovered the derivative, which enabled the unlocking of the secrets of planetary motion and gravitational attraction. Hi, my name is Tom Atwater, and today we will be discovering how to use the derivative to find the slope of the tangent line, as well as the relationship between the graphs of the function and its derivative. Let's start with the definition of the derivative. The derivative of a function f with respect to the variable x is the function f prime, whose value at x is f prime of x equals the limit as h goes to 0 of the quantity f of x plus h minus f of x all over h, provided that the limit exists. Let's do an example where we apply this formula. Let's find the derivative d of x squared dx. So our function is x squared. And we're going to apply this formula to find the derivative of the function x squared. So what we would do is this is equal to the limit as h goes to 0 of x plus h squared minus x squared, and that's all over h. And now what we need to do is expand this binomial. So let me go to a clean screen and do that. So it's the limit as h goes to 0. And if we expand that binomial, we get x squared plus 2xh plus h squared minus the x squared, and that's all over h. So now the x squareds go to 0. I can factor out an h from each of these terms. That gives me the limit as h goes to 0 of h times the quantity 2x plus h all over h. These h's cancel to 1. And we have the limit as h goes to 0 of just 2x plus h. And now, of course, if h is going to 0, we are just left with 2x. So this is the derivative of x squared, 2x. Now, there is an alternate definition that is sometimes useful with other types of problems. So let's take a look at that. The derivative of the function f at the point x equals a is the limit f prime of a is equal to the limit as x goes to a of the quantity f of x minus f of a, all divided by x minus a, provided, of course, that the limit exists. So again, the best way to look at this would be to try an example. So this time, use the alternate definition. We have the function f of x is equal to the square root of x, and we apply this alternate formula. So what we have is the limit as x goes to a of, well, we take x and plug it in, so that's the square root of x. We take a and plug it in, so that's the square root of a, and that's all over x minus a. To simplify this, what we're going to do is multiply the top and the bottom by the square root of x plus the square root of a. So let me move to a clean screen, and we will do that. Okay, so here we'll now multiply top and bottom by the square root of x plus the square root of a over the square root of x plus the square root of a. Now on the top, you can see that that's the difference of two squares. So we're going to end up with, on the top, simply having x minus a. Okay, on the bottom, we have x minus a times the square root of x plus the square root of a. Now, of course, what happens is the x minus a's reduce or cancel to 1. And so now what we have is the limit as x goes to a of 1 over the square root of x plus the square root of a. Now, if x is approaching a, then all we need to do is substitute a in for x, and you'll see that we have 1 over the square root of a plus the square root of a, which of course gives us 1 over 2 square roots of a. And so that is our derivative using the alternate definition. Okay, so we've seen a little bit of the other notations for a derivative. And here are some more notations that we can use to describe the derivative. F prime of x, we can use simply y prime. We can also use dy dx, or the derivative of y with respect to x. Then we have df dx, or the derivative of f with respect to x. And then we have d dx of f at x, or the derivative of f at x. Now, we want to work on graphing the derivative function for a function for which we have the graph. As we do this, keep in mind that the derivative is the slope of the graph. So we will be graphing slopes as y values for our derivative function. So here we have graph the derivative of the function f, whose graph is shown below. Discuss the behavior of f in terms of the signs and the values of f prime, that is, of the derivative. So if we look at this particular graph, we're going to look at these points that are labeled A, B, C, D, E, and F. And what we'll be doing is looking at the slopes of the tangent line. So you can see that we have a line drawn here, and we're going to be looking at that, and we're told that that slope is 4. And as we go to some of these other ones, for example, let's look at C. Although the line's not drawn, I'm going to draw it in there for us now. And that is obviously a horizontal line, which has a slope of 0. Then let's go down to point E, which is this point here, and what we would notice is the tangent line. I missed it just a little bit, but you get the idea. The tangent line at E is -1. Okay, so what I'm going to do is now switch to a picture that's going to show us the function and the derivative. So what I've done for you is this. We have point A, which has a slope of 4. So I have actually put the A prime, the derivative, which is 4, right on 0, 4. Then I took the point B, which has a slope of 1, and that's why it belongs right here. Then C, which we already said had a slope of 0, we graph it right here. Then D, which has a slope of -1, goes down to -1. E also has a slope of -1, so it's down here at -1 for the y value. And then finally, you'll notice that F is going to be the point 6, 0. And that's what we have here. And so then when we draw our graph through those points, you can see that this graph here is a smooth curve, which what we've done is estimated every other point based on the slopes that we actually looked at. And that is the derivative of the original function. Now, we can also sketch the graph of a derivative of a function that is given to us as a set of data points. So what we're going to do is look at a table, which will be on the next slide, and it gives the approximate distance traveled by a downhill skier after t seconds for the interval of time 0 to 10. Make a scatter plot of the data and use that to sketch the graph of the derivative. Then answer the following questions. A, what does the derivative represent? B, in what units would the derivative be measured? And then C, can you guess an equation of the derivative by just simply considering its graph? Okay, now let's look at the table. We have skiing distances. Here are our times from 0 to 10 and the corresponding amount of feet that the skier traveled. Now what I've done is taken this table and I've plugged it into the graphing calculator, and then I'll show you what the result was. Here's the scatter plot of the data on the graphing calculator. So then what I did was I ran a regression on the graphing calculator, and of course it's a quadratic regression. You'll see that it looks very similar to a parabola. So I ran the quadratic regression, and we can see here that it gives you the results. So we would have y is equal to 3.3 x squared minus 0.068 x plus 0.052. And that would have been the quadratic regression. And then what I did was I plugged into the calculator to take the derivative of that quadratic expression and to graph that derivative, and let's look at those results now. Here's the original scatter plot that I talked about, and then here's the derivative. It turns out to be a straight line, and we'll see algebraically why that happens later on. The derivative, we were asked, what does it represent? Well, the derivative here represents the speed of the skier in feet per second. And an equation for the derivative, again, I got this off the calculator. It could be about like 6.66 t, for example, or maybe 6.65 t. But that's something that you can also get from the calculator. Sometimes we wish to know the rate of change, or the derivative, from one side only. And we call these one-sided derivatives. Let's look at how those are defined. The function y equals f of x is differentiable on a closed interval a comma b if it has a derivative at every interior point of the interval. And if the limits, okay, we have the limit as h goes to 0 from the positive side, or from the right-hand side, of f of a plus h minus f of a all over h. And that's considered the right-handed derivative at a. We also have the limit as h goes to 0 from the negative side, or from the left-hand side, f of b plus h minus f of b all over h. And that's called the left-handed derivative at b. And of course, the definitions show how to find the one-sided derivative. But be careful in concluding that a function has a derivative just using one-sided derivatives. And let me show you an example of that. Show that the function has a left-handed and a right-handed derivative at x equals 0, but it has no derivative at x equals 0. So we have the function y is equal to x squared for x less than or equal to 0, and we have that y is equal to 2x for x greater than 0. So let's take a look at that particular function. we are evaluating this at x equals 0. So I need to plug in 0 in place of a. So what we would have is the limit as h goes to 0 from the positive side of 2 times 0 plus h minus 2 times 0. And that's all over h. So now, let's simplify the top here. We have 0 plus h, which of course is just h, times 2. So we have the limit as h goes to 0 from the positive side. We have 2h over h. And of course, the h's cancel, and so the limit is just equal to 2. So that's the right-hand limit is equal to 2. Now, let's find the left-hand derivative. And to do that, let me go to that screen. This time what we have, of course, is h approaching 0 from the left-hand side. And this time we have to use the function x squared. So what we will have is the limit as h goes to 0 from the negative side of 0 plus h squared minus 0 squared all over h. Of course, here, 0 plus h is h squared. So 0 plus h is h, and then we square it, so we get h squared. That's just 0. So what we have is the limit as h goes to, whoops, the limit, let me erase that. We have the limit as h goes to 0 from the negative side of h squared over h. Of course, those h's reduce down, and this is equal to h. And the limit as h goes to 0 of just h, well, h is going to 0, so the limit is 0. And what that means is that the left-hand derivative is 0. And we found already that the right-hand is 2, so the derivatives are not equal at x equals 0. So the function does not have a derivative at x equals 0. Well, now it's time for you to try a problem. Show that the function has a left-hand and right-hand derivative at x equals 1, but no derivative there. And the function is y equals x squared plus x, where x is less than or equal to 1, and it's equal to 4x minus 2, where x is greater than 1. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Let's find out how you did on this problem. Let's first find the right-hand derivative. So to do that, we're going to use the function 4x minus 2. So let's evaluate and plug in 1 plus h because we're looking at x equals 1. So we have the limit as h goes to 0 from the positive side, the right-hand side, of 1 plus h plugged into x. So it's 4 times 1 plus h minus 2. And then we have minus, well, an interesting thing occurs here. We want to find f of 1. Now, I've said we're using the function 4x minus 2, but that's not defined for x equals 1. So we actually have to evaluate for x equals 1 and use x squared plus x because that's where x equals 1 is defined. So this would be minus 1 squared plus 1. And that's all over h. So now, simplify this. We have the limit as h goes to 0 of 4 times 1 plus 4 times h. So 4 plus 4h minus 2 minus 2. And that's all over h. Now, of course, what happens here is the 4 and those 2 minus 2's add up to 0. So I'm just left with 4h over 4, but of course the h's cancel, and we get that the limit as h approaches 0 is 4. So we know that we have a right-hand limit, a right-hand derivative, which is 4. Now what we need to do is find the left-hand derivative. So the left-hand derivative, we're going to use the function x squared plus x. So what that would be is the limit as h goes to 0 from the negative side, from the left-hand side, of 1 plus h squared plus 1 plus h. So that's my x plus x, my x squared plus x. Then we have to subtract from that f of 1, which again is 1 squared plus 1. And that's all over h. So now let's simplify this. We have 1 plus h quantity squared, so that's just a binomial squared. We'll have the limit as h goes to 0 from the negative side, from the left-hand side. 1 plus h squared is 1 plus 2h plus h squared. And then we have plus 1 plus h, and then we have minus 2. And that's all over h. So now looking at this, we can see that the 1, and the negative 2 add up to 0. We have an h and a 2h, which adds up to 3h. So this is the limit as h goes to 0 from the negative side of 3h plus h squared all over h. And now, of course, we can cancel an h, leaving us with the limit of 3 plus h as h goes to 0 means that we get a limit of 3. So the left-hand limit exists, that's 3. We already found that the right-hand limit was 4, but this function does not have a derivative at x equals 1. All right, so if that's the answer you got, you're well on your way to using this formula for derivative. So in today's lesson, we learned about the derivative, 2 different formulas for using that derivative, and how to apply it. Be sure to work the exercises that your teacher assigns, and we'll see you next time.